With grid search, it is possible to tune different hyperparameters at the same time. In the example above, we tuned two different hyperparameters. We tuned the number of components, which belong to the dimensional reduction step of our workflow, as well as the alpha hyperparameter of our ridge model, the model that's actually making the predictions. So what grid search did there is it constructed a two-dimensional grid to search through. And the keys for the values for these keys represent how many points in that axis. So we're saying here, search through, investigate value of 2, 3, 4, 5, and 6. So that's 5 different values. For alpha, investigate 20 different values for a total of 100 different combinations, 100 different candidates to search through. Now you can go ahead and have 3, 4, 5 different hyperparameters to tune, but things are going to get a bit out of hand. We're going to construct a large dimensional space to search through, and the number of candidates are going to grow exponentially. Things are going to blow up. So our training time is going to be going to take a long time. In the example here, only 100 candidates, 8 seconds. But what if we had cranked this up to a larger number, or we had a finer grid in one of the axes? For the alpha space, we're only searching through 20 different values of alpha. We could have said, let's investigate 100 different values of alpha. So we construct a finer mesh, a finer grid along that axis, so that since we have a finer grid, we can perhaps find a better answer to what we currently have. And we have a very complicated workflow, very complicated machine learning models. There are more hyperparameters we want to tune and investigate. So we have to make some trade-offs. We can go ahead and just say, maybe we're okay with having a very small computational grid, or a grid that's not very fine. So we may miss out on some of a better answer. Or maybe we'll go ahead and look at the hyperparameters that we want to tune. Maybe there's some that we can just drop and not tune, or tune them separately. You want to look at the models and determine what are the best hyperparameters to tune, or what are the most important hyperparameters that are going to affect our model's performance, and perhaps just focus on those. We can go ahead and make the assumption that some of these hyperparameters, that there's very little interaction between them, so we can tune them independently. If we do go ahead and tune them independently, in other words, we tune alpha first, but not modify the number of components. We choose the best alpha, and we can choose the best number of components and keep the result of those two different searches. So tune them independent of each other. If we do that, then we have a linear complexity. If we tune them to have interactions, then we have an exponential complexity, which will be very slow when we have more complicated workflow and also a very large training set. Another alternative we can go ahead and do is, let's use a different way to tune these models. Scikit-learn has an alternative to grid search called randomized search. And as the name implies, the way that randomized search is going to do, it's going to take that computational grid, that mesh grid that is constructed through this param grid. But it's only going to sample part of the space. If this computational grid has 1,000 different candidates, and you say only investigate 100, it will only sample 100 of those, 100 random samples, and then try to find the best answer through those. One way you can view hyperparameter tuning is that it is an optimization problem. It's an optimization problem. We're trying to figure out what are the best set of hyperparameters that are going to result in the best error metric or the lowest error metric. So you might be wondering, well, randomized search, since it's only going to investigate a subset of my candidates, it's probably going to do worse than grid search. And yes, it might do worse than grid search, but perhaps it's only going to do slightly worse than grid search, at the cost or at the gain of faster computational time, faster runtime. So let's go through a thought experiment. Let's go ahead and prove to ourselves that randomized search might be a good option at times. Let's say we're trying to find the best answer for our optimization problem. And yes, there's one point in space that's the best answer that we want to investigate, that we want to find out. But let's go ahead and assume that we're okay with if we were to sample a region of our space that is near optimal. yes, it's not the best answer, but it's really close to the best answer, and it's gonna be, just as good enough for our application. And we're gonna make the assumption those near optimal points exist within 5% of our space. Remember, we have an optimization problem. In this case, it's a two-dimensional space. So let's say we have a hyperparameter called alpha, one called beta, and then we can construct our computational grid, and then brute force and find the best one. But let's subsample this space. And the best answer might exist right here. And I'm purposely putting in between our grids. But if we were to sample in this small region, we get it close enough to the true answer, close enough to the best answer. And let's say this represents 5% of our space. Then the probability for me to sample only one point and not sample this near optimal region is 0.95. A 95% chance of failing from sampling from this near optimal region. Let's say I'm going to sample, look for that near optimal region. I'm going to do it n number of times. So for me to fail n number of times in a row to sample at least once in this near optimal region is 0.95 raised to the n power. So then the probability for me to succeed in sampling at least once in this near optimal region is just 1 minus 0.95 raised to the n power. And let's say we want to sample any number of points such that 95% of the time we're going to sample in this near optimal space. So we're going to set the right hand side equal to 0.95. So what this means here is that if we randomly sample our space and we're trying to look for this near optimal region, which we assume is only 5% of our space, and that means we want to find how many times should I sample from this space such that 95% of the time I'm going to at least sample 1 point from this near optimal space. So let's solve for n. So if I solve for n, I have 0.05 on one side and 0.95 raised to the n power. Take the log on both sides so I can solve for n. So I have the log of 0.95 times the log of 0.05. So if I do the math, there's 0.95 there. If I do the math, it comes out that n is approximately equal to 58. So this is sort of the justification behind the randomized search. Of course, there's some big assumptions here. One of those assumptions is that 5% of our space is near optimal. And the nice thing about randomized search is that you can go ahead and have a very fine mesh, increase the number of points as possible candidates, have a finer mesh, such that if the lowest value of our space exist in between the grids, then having a finer mesh, you can go ahead and investigate, get closer to that optimal value. So let's try a randomized search in scikit-learn. So model selection, import randomized search, and we have very similar syntax as grid search. In fact, let me just go and copy paste some things. So I do there. And since I have, I'm going to investigate more values, a finer mesh. So I'm going to say 1 to, let's say 7, 1 to 9. There's 8 values there. This is 200 values. So it'd be, if I do my math right, 1,600 candidates. But since we're doing randomized search, we're only going to subsample. We're going to subsample, only visit a part of those, a fraction of those. Just call this pipe 4. Pass the param grid. Same arguments we use with grid search. Pass the estimator, pass the param grid. How many folds? how many jobs in parallel. You want a status update as you fit the model. Another key parameter is the n-iter, which says how many samples should we take from this constructed grid. I'm going to say 100. It's a grid search. Sorry, I'm going to call this random search. That's X train and Y train. Let's go ahead and print out the score of our test set. Okay, so the R-squared value was 0.59 for the test set. I think for this one it was very similar. Let's just verify. Oh, it's actually not so great. So in this case, we were able to have a finer computational grid, but we subsampled. In this case, it led to a better answer. So keep in mind that you also have access to grid search, but you can also use randomized search to figure out what are the best hyperparameters to use for your model.